Good afternoon. Today I'm going to start off by introducing a new concept, the concept of a metric. So the question that we will address here, where this concept becomes relevant, is one of distances. So let us consider the usual three-dimensional space. In this space, we have 2 points. So one point is the point x, y, z, which has got coordinates x, y, z. And the other point has got coordinates x plus dx, y plus dy, z plus dz. So we have the usual three-dimensional space in which we have 2 points which have these coordinates. And the question that we ask is, what is the distance between these 2 points? Now I am sure all of you know the answer to this question. The distance delta L square or dl square would be more appropriate. So because these are all infinitesimals, dl square is dx square plus dy square plus dz square. So we are working in the usual Cartesian coordinates x, y, z, and these are the 2 points. So let me call them A and B. So we have the 2 points A and B separated by dx, dy, dz. And the question that we ask is, what's the distance between these 2 points? And we all know that the distance dl squared of this line element, so this is the line element, the distance, this is the small line joining these two. So the length of this line, which is the distance between these points, is dx square plus dy square plus dz square. This is what is called the line element. And it is convenient to write this as Gij dxi dxj. So the square of the distance between those 2 points we have written as Gij dxi dxj. So this is just a notation by which we write this expression in short. So this is a shorthand notation for writing this expression. Let me spend a little time explaining this notation. So the notation index, so this is what is called the index notation, which may or may not be familiar to you. Let me spend a few minutes explaining this. So we use xi to denote the 3 components of the coordinate. I runs from 1 to 3. So it has values 1, 2 and 3. x1 is refers to x, x2, this is not x squared, x2, when I takes the value 2, it refers to y, and x3 refers to z. So the index I, when it takes on value 1, refers to the x-axis. When it takes on value 2, it refers to the second coordinate y. When it takes value 3, it refers to the third coordinate z. Okay. So this is the first thing. This is the index notation. The second point is Einstein summation convention. what is the Einstein summation convention? In the Einstein summation convention, if I have two indices ai, let us say I write something like this, where two indices, so ai is something which has got three indices, bi also is something which has got three indices, so it has essentially three components x, y and z. This also has three components x, y and z. Now the index I is repeated. Whenever there is a repeated index, you should sum over all possible values it could take. That's the basic Einstein summation convention. So this is a shorthand for writing A1 B1 plus A2 B2 plus A3 B3. Because the index I is repeated, you should sum it over all possible values. So all possible values are 1, 2 and 3. So this is exactly identical to this. It's just a notation. Okay. So with this digression, let us get back to what we were discussing, the length between these 2 points. So now we know how to interpret this. We have to apply the Einstein summation convention because I and j both are repeated, and applying that we see that this is equal to G11 dx dx1 if you wish. So let me write it as dx1 plus, now you have to sum over all possible values which I and j can take. So G12 dx1 dx2 etc etc. So there will be more such terms. Okay. I and j have to be summed over all 3 values 1, 2 and 3. So there will be 9 values in together, of which 3 are exactly same. So there will be 6 independent separate values. So remember that dx1 essentially refers to dx, dx2 refers to dy and dx3 refers to dz. Okay. Now in this expression, these dxi's, the dxi are the contravariant is a contravariant vector. It's a vector. It should be obvious that it's a vector because it is a difference between, so it's the displacement between 2 points, right? So dxi are the contravariant components of a vector. It's a contravariant vector, and gij is a covariant tensor of rank 2 called the metric. So this is what is the metric. Its role, so this gij that appears over here is what is the metric, and its role is that given a small displacement, it tells us how to calculate the length corresponding to that. Okay. dl square is gij dxi dxj. That's the role of the metric. It tells us how to calculate distances between 2 points. Okay, that's the metric. We need not, okay, I'm not going to go into the details of what we mean by a contravariant vector, covariant tensor, etc. Those of you who have done some amount of differential geometry will already be familiar. If you have not done, maybe you could just look up a little bit and get familiar with it. But we will not go into these details in this course. Okay. Now, I have told you what the metric does. We use the metric to calculate the distance. Now, we already know how to calculate the distance in 3-dimensional space. So, by just comparing this expression, which I have written out here, with this expression, we can identify what are the different values of the metric components. Okay, so let us see. So, by comparing this with this, we see that G11, which is the number that multiplies dx square, what's the value of G11? 1, right? So G11, we read of the metric components, G11 is equal to 1. Now how much is G12? Is there any term dx dy appearing over here? No. So G12 is 0. 12 is equal to G13, 12 is equal to G13, which is equal to 0. So the only non-zero terms that appear in this metric are G11, G22 is equal to G33, and all of them are 1. The rest of the terms are all 0. Okay, so rest 0. This is a rather simple metric. This is the metric of the flat Euclidean space in the Cartesian coordinate system. I can also write this metric in matrix form. I can write the metric in the form of a of a matrix. So let me do that. Gij can also be written in the form of a matrix where the I index varies in this direction, the j index varies in this direction. So this refers to the 1 1 term. The 1 1 term has a value 1. I takes values 1 2 3, j takes values 1 2 3, right? So this is the 1 1 term. This will be the 1 2 term. 1 2 term we saw was 0. 1 3 term was 0. So we can straight away write down the components of this metric in the form of a matrix which has these values. Okay, and the metric is a symmetric. It has the property that it is symmetric. Okay, so this is the metric. It is symmetric. In terms of the components, it means that if I interchange the rows and the column, if I interchange these two, the rows and the column, if I just flip it around the diagonal, if I interchange the rows and the columns, the matrix remains the same. Okay, so the metric is a symmetric matrix, which we use to calculate the distance. And we have worked out what the matrix is, what the metric is, in a simple situation where we have the usual three-dimensional Euclidean space in Cartesian coordinate system, in a Cartesian coordinate system. Okay. Now, the metric plays a very important role if you are dealing with curved spaces. Or if you are dealing with the usual Euclidean space in some curved coordinate system. So, in either of these situations, the metric becomes different, right? So, if you are dealing with just a usual Euclidean space Cartesian coordinates, there is really no need to introduce a metric, but it becomes very relevant when you are dealing with curved spaces. The space itself is curved, or if you are using a curved space in coordinate in the usual Euclidean space. So, let me take up examples. The first example is a spherical polar coordinate system in 3 dimensions. So, let me discuss a spherical polar coordinates. So, we have the usual Euclidean space, and these are the Cartesian axes x, y and z. But instead of using these 3 coordinates, we could use a different set of coordinates to a point. So, if this is a point, we could describe it by its x, y and z coordinate, but instead we could also use spherical polar coordinates. What are these spherical polar coordinates? The first coordinate is the distance to this point, r. The second coordinate is the angle that this line, that this point makes with the z axis. It's called theta. And the third coordinate is if I project this point onto the xy plane, the angle that it makes with the x-axis, which is called phi. So in the spherical polar coordinate system, we have three coordinates r, theta and phi. So let us again address the same question. I have 2 points. One point has got coordinates, the same points, let us say A has now got coordinates r, theta, phi, and B has coordinates r plus dr, theta plus d theta, phi plus d phi. So it's a different point, slightly shifted. So this is A, and we have another point B, whose coordinates are slightly different, right? But now instead of giving the Cartesian components, I have given you the components in this polar coordinate system, and we would like to now calculate the distance between these 2 points. Now I am sure it is familiar, it is known to you that the distance, again you apply the same Pythagoras kind of theorem kind of thing, the distance between these 2 points, dl squared, let me write it here, dl squared is d square r plus r square d square theta plus r square sine square theta d square phi. Right? This is how you would calculate the distance between these 2 points in this spherical polar coordinate system. And if you are not familiar with this, it's easy to, you could easily check that this is correct, because you can break up this separation into 3 components, one along the r direction, one along the theta change in the, one due to a change in r, which would be like this, one due to a change in theta, which would be like this, and a third one due to a change in phi, which would be into this inside over here. Okay, and these are all perpendicular, so you have to just add them up. Okay, so now you see that the length, the way you calculate the length is not just dr square plus d square r plus d square theta plus d square phi. There are these extra terms over here, and identifying this as the first coordinate, this as the second coordinate, this as the third coordinate, we can write down the metric. The metric Gij in this case, this is the line element, the metric Gij in this case has got components 1, then there is no r theta term, there is no r phi term, so 0 0, then we have 0 r square d square, the term that multiplies d square theta, and we have 0 0 r square sine square theta. So now we see that the metric is not such a trivial thing. It is not just ones and zeros, not a diagonal matrix. It is a diagonal matrix, but not the unit diagonal matrix. It has got r square and r square sine square theta over here. So it is something more complicated, and you have to use this when you wish to calculate the distance between 2 points. So the distance between 2 points you could write as dl square is equal to gij dxi dxj, and you have to use this metric to calculate the distances. Okay, so this is a situation where you have a flat space, but you have a curved coordinate system. Now let me consider a different situation where I have a a curved space. Now a curved space, the simplest example would be in 2 dimensions. So let me consider the surface of a sphere. So a curved space in 2 dimensions, a 2-dimensional curved space, not 3. So we have 3 dimensions here, and in this three-dimensional space, we have a two-dimensional surface, the sphere, which is embedded here. And the sphere has unit radius. So we have a sphere of unit radius, and the surface of the sphere, it's called S2. The surface of a sphere, like the surface of the earth, which we shall refer to as a sphere. Okay. So S2, the surface of the sphere, is a two-dimensional space, which is curved. It's not a flat space. Now the question is, what are the appropriate coordinates to use on this surface of a sphere? For example, on the surface of the earth, what would be appropriate coordinates? Now the theta and phi, which we had introduced earlier, would be very appropriate coordinates to use over here. So we could label each point on the surface of a sphere using theta and phi. Now the question arises, if I have 2 points with different theta and phi, let us say infinitesimally different theta and phi, what's the length between these 2 points? Remember that the sphere has unit radius. So the length of the line of the vector joining the distance between these 2 points is d square theta plus sine square theta d square phi. I have 2 points on the surface, so they will have different theta and different phi, and the distance between these points is d square theta plus sine square theta d square phi. R doesn't change, that's the main thing, that we are on the surface of the sphere. So we can say that the metric, we can write this as Gij dxi dxj. Now I and j takes values 1 and 2 only, and the metric is 1 0 0 sine square theta. So this is a curved space, and the metric is something different from the identity matrix. So in general, in some arbitrary curved coordinates, or in a curved space, the line element dl square will be written as Gij, where the metric components are themselves functions of the coordinate. It varies from place to place, into dxi dxj. Okay. So in general, you could have some arbitrary matrix. The metric could have, the components of the metric could be functions, arbitrary functions of the coordinate, as long as this Gij is symmetric, and in some general curved coordinate system, or in some general arbitrary curved space, this is the general form. So the metric is now, the components of the metric are now functions of the coordinates. Let me give you a very simple problem which you should try out. The problem is as follows. So the assignment, it's an assignment which you should work out. Consider two-dimensional space. In this two-dimensional space, you could have coordinates which are like this. The x-axis is here, and the y-axis, instead of being perpendicular, is at 60 degrees. So obviously, the distance between 2 points is not delta x square plus delta y square. There will be some difference, and that difference will make a change in the metric. So you should find out what is the metric, what's the line element, calculate the line element, and the metric for the flat space in this non-Cartesian. So it's a coordinate system which is linear, but the axis is not, the two axes are not perpendicular to each other. So find out the components, what are the components of the metric in this coordinate system. So in the past few minutes, I have told you what we mean by a metric. What's the utility of a metric? It essentially is to be used to calculate distances between points. Now, let me move on to something else. It is very useful and convenient to combine space and time into what a four-dimensional space called, into a four-dimensional space which you refer to as space-time. Okay, so it is useful to introduce something called the space time. Okay, it's a four-dimensional space. It has got 4 dimensions. It's a space with 4 dimensions. The fourth dimension here is time. So we can label points in this four-dimensional, in the space-time, using 4 coordinates. The first coordinate is going to be x0, which is c into time. The second coordinate x0, then we have x1, which is x, x2, which is y, and x3, which is z. Okay, so we are introducing the concept of space-time. So we are combining, taking a kind of unified picture where we talk of space and time on the same footing, or nearly the same footing, and we refer to it as space-time. It's a four-dimensional space. Points in this four-dimensional space are labeled by the time and the position. So this x0 labels the time, x1, 2 and 3 labels the position, and we can refer to this as x mu, where mu takes values 1, 2 and 3. So xi refers to the space, x mu refers to, 0, 1, 2 and 3. Okay, refers to space-time. So points in space-time are labeled by the time and the position. Now events, so points here correspond to events. Events are labeled by the position they occur and the time at which they occur. So somebody is born. So to completely specify the event, you have to tell the position where he was born and the time instant when it occurred. Right. So this space-time, the points in space-time are events. So events make up the points in space-time. Okay. Now the next concept that I will introduce is a space-time diagram, which pictorially represents this space-time. So it's a method for pictorially representing events and the relation between events that occur in the space-time. So space-time diagram. So a space-time diagram is a method used to represent events and the relation between events. Now it would be a diagram of 4 dimensions. Drawing 4 dimensions on this 2-dimensional paper would be very difficult. So usually we suppress 2 of the dimensions and draw space-time diagram only in 2 dimensions. So we show only one of the spatial dimensions, could be x, y or z, let us say x, and along the y-axis we show the time x0, which is ct. So different points on this diagram correspond to different events. So let us now consider various possibilities on this space-time diagram. There is an observer at rest. A person is sitting at rest. You are sitting in your chair at rest. So on this space-time diagram, your x coordinate would be fixed, x1 or x would be fixed. With time, everything evolves with time, so it would be a straight line like this. Vertical straight line. This is a particle at rest, an observer at rest. It's a vertical straight line. This would be another person at rest. Okay, vertical straight line. Now, next, let us consider an event. The event that we will consider is that this person, this observer sitting over here, sends out a photon, a light, sends out a light pulse, a photon. Now, light, we know, sends out a light signal. So, we know that this travels at a well-defined speed, and the speed is c. So, the light that is emitted from here, say he switches on a bulb, the light that is emitted travels at the speed c, and it moves along the trajectory ct, x is equal to ct, where c we know is the speed of light, is the 3.08, 3.0 into 10, 3 to 10 to the power 8 meters per second. Right. So, the light which is emitted from here on this diagram moves at 45 degrees, and this is another event in the future where the observer over here receives this light. So, the propagation of light in this space-time diagram is depicted by lines at 45 degrees. A 45 degree line starting from here shows a light ray, a photon being emitted from here and propagating forward. Now, if another particle is moving slower than the speed of light, then its trajectory would be a line starting from the same point, let us say, but moving like this, steeper. So, the red line shows you the trajectory of a photon, and the black line shows you the trajectory of a particle which moves slower than the speed of light. Okay. Now, this is a space-time diagram. Now, in this 4-dimensional space-time, we have a generalized concept of the length called the interval. So, the interval d, so let me define what the interval is. So, consider two events. The first event is A, which occurred at the time x0. It has coordinates x0, x1, x2, x3, dx ct, or in other words, it occurred at the time t at the position x, y and z. So, we use these to label that event. This event could be that the photon is emitted from here, light is emitted from a star. And another event B is this, let us say this event, they are infinitesimally close. So, the light which is emitted from the star, let us say it reaches some other point, it is observed by you. Okay, that would be a different event at a later time. So, let us consider two events which are infinitesimally close. So, the second event B has coordinates c t plus delta t or dt, x plus dx, y plus dy, z plus dz. Now, between these two events, we define the interval ds square. For these two infinitesimally close events, we define the interval ds square as c square dt square minus dx square minus dy square minus dz square. Okay, so given any two events, which are infinitesimally close, we can calculate the interval between these two events as ds square. Okay, the ds is the interval. We could calculate the interval ds as c square dt square minus dx square minus dy square minus dz square. Now, what is the utility of this definition? Why have we defined it like this? Let me briefly discuss this. The first point, that people who have done special relativity, some amount of relativity, will be familiar with this. Okay, I'll just give a brief discussion for those who are not familiar, and I will suggest that you look up books on relativity if you would like to know in more detail. The first thing is, along this, if the two events that we are considering are along the light ray, the propagation of light, if these two events are this event and this event, then the interval ds square is 0. Why is it so? Dx square plus dy square plus dz square, what does it tell us? It is the distance squared. Now light travels at a fixed speed c, so in the time dt square it will travel exactly this distance, so these two terms will cancel out. Okay, so for light, d square is, or ds is 0 for two events along a photon's trajectory. Now let us, these are called null. So this is called null, a null trajectory. It has 0 length effectively. See the length, this is like a length, but the distance between 2 points in the Euclidean space can never take value 0 or become negative. Here it has the property that it can be 0 even though the points are different. It could also be negative. Okay, now, so this is not the familiar Euclidean space. This space-time is not Euclidean. That's a point which you must have realized by now. Okay, now let us consider two events which are along the trajectory of a particle that moves slower than the speed of light. Suppose the two events are along this trajectory of a particle at rest, an observer at rest. For such an observer, this dx and dy and dz are all 0. Only time evolves. ds square is positive. A particle which is moving at a speed slower than the speed of light, in a time dt, obviously the distance that it will cover is less than c dt. So for a particle along a is greater than 0 along the trajectory of a particle with v less than c. Two such events are said to be time-like. Why is it said to be time-like? ds square is positive for an observer at rest, for a particle at rest. For a particle at rest, only time changes, right? So ds square is positive for such a particle, which is why when ds square is positive, it's referred to as time-like. If ds square is less than 0, it is said to be the interval is said to be space-like. So if I had two events, say one event here and one event here, for which the time is the same, there is only a change in x, y and z, these two events would be space-like. So intervals, so the separation between 2 points can be classified based on their interval, and the intervals are said to be either null, time-like, or space-like based on the value of ds square. Now, Einstein's theory of special relativity. What does Einstein's theory of special relativity tell us? It says that all inertial frames are equivalent. Okay, this is a point which I should have mentioned earlier. Let me just go back a little bit. Before coming to Einstein's special theory of relativity, let us consider the length between 2 points. If I change my coordinate system, the value of the coordinates corresponding to A and B will change. If I choose a different coordinate system, the value of the coordinates corresponding to the point A and B will change. But does the length of the separation between these 2 points change? No. Right? The length is an invariant quantity. The length does not change. Not only if I do a rotation like this, even if I go to a spherical polar coordinate system, the length between 2 points doesn't change. In a spherical polar coordinate system, for the same 2 points, the length does not change. So the length between the distance between 2 points is an invariant. This is an invariant. That's a very important thing. Which I forgot to mention. If I go to a different coordinate system, dx, the components of the coordinate between the corresponding to the separation between those 2 points will be different. The metric will have different values. But the length between those 2 points is an invariant quantity. So the length is an invariant quantity. The metric may change, the coordinates may change, but the length is an invariant quantity which is actually used to determine what the value of the metric is in a different coordinate system. Okay. So that is the property of the length. Now here I am claiming that this interval plays the role of the length, is equivalent, it plays a role which is somewhat analogous to that of the length. Then if it is indeed so, then this must be an invariant. It turns out that Einstein's theory of relativity, in Einstein's theory of relativity, all inertial frames are equivalent. And so all inertial frames are equivalent, and the speed of light is invariant, is the same in all inertial frames. That is the first assumption. So, and this is an observed fact on which Einstein's theory of relativity is based. Okay. Now, with this, let us come back to this space-time diagram. I am considering 2 events, and I would like to calculate the interval between these 2 events. If I go to a different coordinate system, the coordinates corresponding to these events will change. So let us consider the same 2 events. Let us consider these 2 events. This is light being emitted from a point at a time. This is the light being received by somebody at some other place at a different time. Light travels at a fixed speed c. Now suppose I go to a different inertial frame. What do I mean by a different inertial frame? An observer who is moving, let us say, with a constant speed with respect to the one where I was earlier. In that coordinate system, this will occur at a different position at a different time. This will occur at a different position at a different time. But the light signal propagates at exactly the same speed. So in that coordinate system, if I again calculate ds square, I will get a new dt prime, I will get new dx, dy, dz, but the light propagates at the same speed, so ds square will continue to be 0. Right? So it is obvious that for a null two events, the interval between which is null, it will be null in all frames of reference, all inertial frames of reference. That is because the speed of light is a constant, invariant. Now you can show, I am not going to give you the proof, but you can show that not only is this true for null intervals, it is true for in general. So the interval is invariant. It is the same, it has the same value for two events. If I calculate the interval in different frames of reference, for the same two events, if I calculate the interval in different frames of reference, the value of the interval is going to remain unchanged, just like the length. So the coordinates corresponding to these events may be different in different inertial frames, but the value of the interval is like the length, it is going to remain unchanged. Okay, that's the first point. The second point is no signal. Einstein's theory, special theory of relativity, is based on the assumption that no signal propagates faster than c, than the speed of light in vacuum. Coming back to this picture, what we see is that if I send out a signal from this point, it can only propagate outwards inside, or let me redraw this, in the space-time diagram. This is an event, an observer, say at a certain time, sends out a signal. So he can send out a signal only, any signal that he sends out, the distance it can propagate at say this time is going to be between this and this. No signal can propagate faster than this. So this observer over here, this person sitting over here, at this time, if he sends out a signal, it cannot reach here because that would be moving faster than the speed of light. So all of these events over here inside this are causally connected to this event over here. Any event outside, for example this event, is not causally connected to this. These two events, okay, so this event cannot causally connect this event, cannot causally influence this event. Okay, I hope I am able to get the point through. For example, the sun explodes. If the sun explodes at this instant, the life on earth will be destroyed, not instantaneously, it will be destroyed after a certain time. How much time is that? It is the time that the light signal takes to propagate from the sun to us. If there is a supernova explosion on a very distant star, then I will not know about it instantaneously. Neither can that influence any event on the earth instantaneously. There will be a time interval after which it can influence events on the earth. Okay, so this is what we mean by causal connection. So two events are, if they can be related by cause and effect, if it is plausible, then they are said to be causally connected. Okay, But if two events are so far apart in space that light signal cannot propagate between them within the time that you have, then they are said to be causally disconnected. There can be no causal relation between them. Okay. So this event and this event are causally disconnected. So what we can say is that null events, this defines the limit of causal connectivity. Time-like events are causally connected, space-like events are not. Okay. Now if you look at these two lines in 3 dimension, they will propagate in both, in all 3 directions, x, y and z, and there this is referred to as the light cone. It will be a cone in this 4-dimensional space-time, because we have to take into account the y and z axis also. So it's going to be a cone which is referred to as the light cone or the null cone. Right? If you think of the y axis in this direction, it will be a cone like this. Z axis is hard to imagine simultaneously. Okay, and any signal that you send out, that comes out from this point, will propagate inside this light cone. Similarly, if I ask the question, what are the events in the past that could have influenced this? That will be the past light cone. This event could not have influenced this in any way. Okay, because a signal that propagates out from here will propagate out like this. So the space-time diagram is a very convenient way to denote causal relation between events, the propagation of light rays and things like that. So the points that I have made is that in this 4-dimensional space-time, we have this interval. We have this interval which is somewhat analogous to the length in this 3-dimensional space. It is an invariant, and its value doesn't change from one coordinate system to another. Now, this is as far as Einstein's theory, special theory of relativity, is concerned. Now what happens, Einstein's special theory of relativity does not incorporate gravity. Now Einstein's general theory of relativity, gravity manifests itself as the curvature of space-time. So the space-time that I was talking about till now was flat. It had no curvature. So in the absence of gravity, the metric Gij has components 1, 0, 0, 0, then minus 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Right. That's the metric, and I have already written down the line element. Now what gravity does is that it introduces curvature in space-time, and in the presence of gravity the whole of space-time is curved. So in such a situation you will have some other metric G, sorry, not Ij, G mu nu. This also will be mu nu, not Ij, because we are working in 4 dimensions now. G mu nu, which will be in general a function of the position. So let me give one example of this, of how Einstein's theory incorporates the effect of gravity. So let us consider a situation where I have a weak static gravitational field. For example, I have a massive object like the Earth or something like that, and this produces a gravitational field, but the gravitational field is weak. It doesn't produce any enormous gravitational effects. By what I mean by weak, I shall quantify just now. So the question arises, what is the metric? So the gravitational forces are now in the metric. So all the gravitational forces are now in the curvature, and the gravitational effects are now in the metric, because the metric has all the information about the curvature of space-time, all the geometrical information. So in the Einstein's theory of relativity, the gravitational field is there in the metric. So let me write down what the metric is, what the line element is in the weak static gravitational field around such an object like the Earth. Okay, the line element is 1 plus 2 phi by c square dt square minus 1 minus 2 phi by c square this line element, this is the line element in the space time in a weak static gravitational field. The space time is not flat. If this phi were 0, the space time would be the flat familiar space time. Now, in the presence of a gravitational field, there is curvature in the space time, and in the Newtonian theory, we represent the gravitational field by a potential, a gravitational potential. So that gravitational potential now appears in the metric. Okay, so the familiar gravitational potential is this phi that occurs over here in the metric, and this is the metric of a curved space-time. In the Newtonian picture, we think of this phi as being the gravitational potential, whose gradient gives you the acceleration, minus grad phi gives you the gravitational acceleration. In this Einstein's theory of general relativity, the space-time is curved, it is no longer flat, and the metric gets changed. As we have seen, in a curved space, the metric is changed. So in a curved space-time also the metric would be changed. And the metric is changed in this way so that the gravitational potential is what is responsible for the changes in the metric. Okay, so the point I am trying to get across over here is that in Einstein's theory of general theory of relativity, the gravitational effects manifest themselves as the curvature of space-time, and all the information about these gravitational effects, the gravitational forces, is there in the metric. The metric changes, it is different for different curved spaces. So it will be different for different curved space-times also. So all the gravitational information is there in the metric. So let me stop over here for today. I have very briefly tried to give you a picture of Einstein's of the geometry of space-time and how it incorporates gravitational fields. In the next class, we are going to discuss the space-time metric, the cosmological space-time metric.